Thank you very much. So I'm a professor at Worcester Polytechnic Institute. We're in Worcester, Mass, an hour west of here. We're a private research university there. And most of the work I'm telling you about today is government-funded research through the NextFlex and FlexTech programs, Department of Defense funded research. And my interest is in materials and processes for printed, stretchable electronics and sensors. And this glove and sleeve human-machine interface that I'm going to describe is sort of a good way for us to study these materials and processes, kind of a good platform or demonstrator for us to see what these materials and processes can do. So it's really nice to see all the different people at the show who are showing different ways of making things with different materials. So the first half of the talk is going to focus on the human-machine interface glove that we've done in a recent FlexTech project. And then that's going to motivate the second half of the talk, which is on liquid metal circuits and sensors, which is kind of newer work that we're doing. So why did we pick a human-machine interface glove specifically? Well, it's useful for a lot of things. You can teleoperate robots, you can train robots, you can have hands in virtual environments for AR and VR. And it really is quite a demanding application because whatever you make on the hand has to be very, very flexible, stretchable. Can't be stiff. It has to be thin. And so anything that you come up with that would work really well on a glove can have a lot of other applications in health, medical, thermal, etc. This is a quick look at the glove that we worked on over the past few years. It's a wearable, sensorized glove and sleeve that is tracking the motion of your fingers, your hand, your lower arm and upper arm. And over the top of that, there's a haptic layer that provides, it's a pneumatic haptic layer that provides force feedback to your fingers. And it's all controlled through a backpack that has the microcontroller, power, pneumatics, and things like that. Here you can see my student is teleoperating a robotic arm and hand to do a pick and place. And he's getting the force feedback from the robotic gripper into his fingers through the haptic muscles on his finger. But today, mainly, I'm going to focus on the sensor layer of this. So this is what that looks like. So underneath the haptic layer, there's the sensor layer, which is integrated onto a stretchable fabric, so a spandex fabric in this case. And it consists of, as you can see, stretchable printed silver traces that carry power and data all along the length of the sleeve. And then there are a bunch of different sensors. So there's printed sensors on each finger, which measure the flexion of the fingers. And then there are IMU measurement motion sensors on the hand, the lower arm, and the upper arm. And the finger flexion sensors are being read out by that flexible PCB on the hand, which has an IC that's doing the analog to digital conversion. And all that data is getting brought back up to the shoulder where it gets sent to the microcontroller. And so just a view of, this is the shoulder of that, and you can really see how much stretch there is when you do a full flex. So we estimate it's around 40%. And so that's really where you have to have a really stretchable material. And you can also see that a little bit close up of how the finger flexion sensors are connected to the flexible PCB that's reading them out. Looking at these stretchable traces, the way we did these was printed stretchable silver, and no matter what silver you're going to use, its resistance is going to increase as you stretch it. And so we have a pretty aggressive testing regime here. It's 40%, stretching it to 40% for 1,000 cycles repeatedly, 4 seconds per cycle. And so the resistance does creep up, but if you build up the number of layers and the width, in this case, 2 millimeters wide, 4 layers thick, and if you add a serpentine pattern onto it, which further relieves stress, you can, even though the resistance is increasing by a factor of 5 over this very aggressive test, the total resistance is still less than an ohm per centimeter length of the trace. So that satisfies our requirement for carrying power and data over this pretty long length, even though you have this aggressive stretching going on. Here's a quick view of what some of the IMU motion sensors look like and what our USB connector looks like.